Hello, today we'll be talking about Dijkstra's algorithm. It is used to find the shortest path between the source vertex and all the other vertices present in a directed graph. Now, we'll walk through an example to find the shortest path from the source A to the vertices B through E. So we initialize an unvisited list basically containing of all the vertices A through E. We also initialize various distances for our graph. Since A is the source, we're going to have the initial distance as 0 for it. And for the other vertices, since they are not explored yet, we're going to have the initial distance as infinity. We're also going to have the previous node, which is currently undefined. This will help us identify the shortest path present. Now let's start off with the iterations of our algorithm. We're going to look for the vertex with the minimum distance in the distance matrix. In this case, it's going to be our source node A, as it's our first iteration with the distance 0. So now A has two neighbors, B and C. We're going to look at these two neighbors and going to update the distances for them accordingly. So B is at a distance of 1 and C is at a distance of 5. The initial distance of B was infinity, and the current distance from the source is going to be 1 plus a distance of source, which is 0. So the new distance is going to be 1. And similarly, for C, we're going to have a distance of 5 plus the initial distance 0, which is going to give us 5 itself. We're also going to update the previous node as we start off with the source A. So the previous node is going to be A itself. Moving on, since A has exhausted all its neighbors, we can remove it from our unvisited list. We're then going to look for the next smallest vertex with the minimum distance. In this case, it's going to be B, which is at a distance of 1. So B has two neighbors here. As you can see, it has a neighbor C and it has a neighbor D. C is at a distance of 2 while D is at a distance of 1. Now, the total distance from the source for C is going to be basically the distance of B plus the length of the distance between B and C, which is going to be 1 plus 2. This distance is 3, which is lesser than our initial distance 5. So we're going to strike that out and we're going to put in a new distance 3 here. At the same time, we'll also be updating our previous node as a new path goes through B. Next, for D, the distance is going to be 1 plus the distance from B to D, which is going to be 1 again. So 1 plus 1, 2. That is lesser than the infinity, which is the initialized value, and hence we're going to have the new distance as being 2 for D. We're also going to update the previous value as being B. Since B has no other neighbors, we can strike it out and look for the next smallest vertex. So the next smallest vertex is going to be D with a distance of 2. So D has only one neighbor E. So E is at a distance of 2 from D, and hence the distance for E from the source is going to be the distance of 2, which is 2, plus the distance between D and E, which is again 2. So 2 plus 2, 4. So the distance of E from the source is going to be 4. With this new distance, we can also update the previous vertex as being D. D has no more neighbors, and hence we can strike it out from our unvisited list. We move on to the next, which is going to be C in our case with a distance of 3, which is lesser than the value for E. So C is currently having only one neighbor, which is D here in our case. D is at a distance of 2 from our source vertex, and at the same time, D is at a distance of 2 from C. The distance of C is however 3 from the source, and hence the total distance is now going to be 3 plus 2, 5, which is greater than the original distance, and hence we are now going to update that. We are going to move on to the next vertex, which is E. As E has no other neighbors, we won't be able to update anything, and hence we're going to strike that out as well. With this done, we now have a final distance matrix, which is the shortest distances, and we also have the previous node, which explains the path to us. Let's visualize the same and see how the path works. So A is at a resistance 0, which is basically the source node. Then we have B, which is at a distance 1, and the previous node being A, so that we have the edge connecting there. Next we have C, which is at a distance of 3 and it's via B. So we can strike out the edge connecting A and C. Next, D is at a distance of 2 from the source and it's via B. So we can remove the edge connecting C and D now because it becomes redundant, and the shortest path is going to be via B. And finally, E is at a distance of 4 and it's going to go via D. So we have E to D here. With this, we have our shortest path, and also we have the distances in our distance matrix here. Now, where is Dijkstra's algorithm used? Dijkstra's algorithm is commonly used in computer networking architectures for, say, routing and path planning. At the same time, it is used multiple places in linear programming for, say, identifying the most optimum route and so on. So that was a brief about Dijkstra's algorithm. I hope you have a clear understanding of this. Thank you.